So now we come to conservation laws. This is chapter 4 in Kundu, and these are our main tools that we use to calculate flow fields. And the first conservation law that we come across is the conservation of mass. And the conservation of mass really is the simple concept that mass is typically neither destroyed or created. For the approximations that we need for fluids, so ignoring nuclear processes, etc., all the particles that we started out with exist for the duration of our study period. And mathematically we can describe this as follows. For a material volume, we can simply write that a certain amount of mass, which can be written as the density integrated over a volume, that the change of this, d by dt, is 0. And so this is the material derivative, meaning that as this fluid element of volume V flows with the flow field, that's what material volume means, the number of particles in it are conserved. So you can think of this as a very, very stretchy balloon where the area A is the boundary and the volume V is whatever is contained in it. And this balloon has no particles going in or out, but it will deform as it goes with the flow. So there is no mass in or out. And in chapter 4.2 for Kundu, the book provides a derivation of the differential form of this conservation of mass equation. So I'm not going to go through it here, but I encourage you to look it up. So 4.2 in Kundu. And so this here is the integral form. So all the conservation laws can either be written in integral form or in differential form. And integral forms are useful if you're considering a certain sized volume that is deforming or moving with the flow, whereas the differential forms are useful if you're considering a certain point. So the differential form of the conservation of mass concept is given as follows: d rho dt plus the divergence of rho u, and that has to be 0. And this equation is quite important. We'll use it throughout the rest of this course, and it's called the continuity equation. And this term here, the second term, is called the flux divergence term. In index notation, we would write this as d rho dt plus d by dxi of rho ui equals 0. The divergence term is also sometimes called the transport term. And it basically means how much mass you're losing at a given point due to that divergence of the flow. And if you integrate over a large enough volume, then as long as there's no sources or sinks at the boundaries, then these terms, these transport terms, will vanish. Now we can rewrite this slightly differently. If you recall the definition of the material derivative, d by dt is just d dt plus u dot grad. So if we have the material derivative of density, d rho dt is d rho dt plus u dotted with grad rho. And now we can write the divergence of rho u as rho grad dot u plus u dotted with grad rho. And so you can see that this term here is the same. So really, u dotted with grad rho is just the divergence of rho u, which is the mass flux, divergence of mass flux, minus rho divergence of u. So we can plug this expression into here, and we are left with d rho dt, the material derivative is just d rho dt, the change of rho over time, plus the divergence of the mass flux, minus rho, the divergence of the flow field. Now this is my equation 1. Let me label this equation 1. Copy this onto my next page. And then the continuity equation is simply d rho dt plus the divergence of the flux is 0. So this is my equation 2. And if you compare these two, you'll find that this term and this term are actually the same. So my material derivative of the density is simply rho times the density times the divergence of the flow field. Or in other words, d rho dt plus rho grad dot u is 0. So that's an alternative way of writing the continuity equation. So now we realize that for constant rho, i.e. incompressible materials, like for example liquids approximately, water is roughly pretty much incompressible. For incompressible materials, d rho dt has to be 0 because rho is constant. So therefore, if this term here is 0, then we realize that the divergence of the flow has to also be 0. Now, for incompressible flow, which is a little less restrictive, we just say that the density doesn't really change in the volume element that we're interested in. So you can have rho as a function of x and t, but the density of the element, the given fluid element that we follow around, doesn't change. So in this case also divergence of u has to be 0. So this is, for example, a pretty good approximation for gases that have velocity less than 100 meters per second. So air in our classic room setting is approximately governed by incompressible flow.